Today I want to talk about the definition of a derivative. Now, I labeled it part one because there are two definitions of a derivative that you'll encounter in your calc class. Today we're going to cover one, and then I have a second video that covers part two that you can take a look at. Now, to start off, so that we are on the same page of what a derivative is, I said that it was an instantaneous change of a function. And all that means is what is the behavior, you could say, of a function at one point in time. Now, I want to start, before we start talking about the calculus piece, by just revisiting something that we're familiar with, which is the average change of something. Like we said, position, if we say position is x, and then velocity is v, right? Velocity, the average velocity, is defined as the change in x over the change in time. Maybe you have seen this before, maybe you haven't, but it's okay. I'm going to explain this a little bit. All the change in x means is it's how much has my position changed. So if I start at point A and I go to point B, right? If I subtract point A from point B, so say I start at the 10-yard line, right? That's my initial position, and I run to the 40-yard line. So my final position is 40, and my initial position is 10. So my change in position was 40 minus 10, which is 30, right? So we can say that my final position, or my change in position, is my final position minus my initial position. Then the change in time is the same principle. If I start at the 10-yard line at time is 4 seconds, and I reach the 40-yard line by time is 6 seconds, then my change in time is 6 minus 4, which is 2. So my change in time is my final time minus my initial time. The bottom line here is that there are some very similar things between this definition of a derivative and the average rate of change. And that makes sense because, well, a derivative is just an instantaneous change. All right, now we're going to dive into things a little bit. So I want to start off with the fraction part of this definition of a derivative right here. We're gonna define these 2 points, f of x plus h and f of x, on our graph. Now we can pick any position. I'm just gonna say right here, and we're going to call this point f of x. And this position on the x-axis is just x. The second point we're gonna define, right, is gonna be f of x plus h. Now, all we're doing is we're saying, hey, let's move some value h units along the x-axis to reach our other point. And this point is going to be x plus h, right? Because we started at x and we moved an amount of h, right? We moved towards this point h amount. So this point is going to be x plus h. Right, and if we're going to write what the function value is, well, if we're trying to figure out what the value is at x plus h, well, for our sake, that's just going to be f of x plus h, right? Because at the point x, our function value is f of x, and at x plus h, our function value would therefore just be f of x plus h. The same way as if we added b, and we said I had a point x plus h plus b, the function value would just be f of x plus h plus b. Whatever you have on the x-axis, when you plug it into the function, in our case, you don't get a number, you just get f of whatever that point was. Okay, now, we define what our points are, and so now what we're going to do, let me move this down a little bit more, we're going to take our average change of f. So we'll say that our average change is just g of x. I'll say average change of f of x. Now, the average change of f would just be, right, the change in f of x over the change in x, right? Similar here where we had the average velocity was equal to the change in x over the change in time, g of x is equal to the change in f of x over the change in x. And again, we just define g of x as the average change of x. Now, like we said at the bottom with our example with position and velocity, the change in x is the final value of x minus the initial value of x. So the change in f of x would be the final value of f of x minus the final value, or the initial value of f of x. Similarly, the change in x would just be the final value of x minus the initial value of x. And if we look at our graph, our final value of f, our final value is going to be the one farthest along the x-axis. It's going to be our one of higher quantity. Say we're traveling along this graph, right? The final place I get to is f of x plus h, and the initial one is f of x, right? So our final position, or our final value, I should say, of f of x, not to get confused, is f of x plus h. And our initial value of f of x is f of x. Now, our final value of x is going to be the point where we are at our final value of f of x, which in this case is f of x plus h. Again, f of x plus h is just the value of f of x when we move h in this direction. So if our final f of x value is f of x plus h, then our final x of x value is going to be where we get that f of x plus h value, which is at x plus h. So our final value will be x plus h. And we'll subtract our initial x value. So if this is our final x value, then our initial x value is going to be here. And that makes sense because our initial f of x value was f of x, and f of x is the value of f at the point x. So our initial x value is just x. Now you'll see that what we just drew here with our change, our average change of f of x, is that this fraction looks very similar to this fraction down here. And that's because they're both average changes, right? The average velocity we said was the average change of the position. Likewise, the average change of f, which we said was g of x, is just the change of f over the change of x. And the change of f is f of x plus h minus our initial value of f of x, which is just f of x, over our final x value, which was x plus h, minus our initial x value, which was just x. Now, I'm going to erase our comparison here. So I want to simplify this a little bit now, right? So if we continue to write this as g of x, and we'll say again, g of x is just the change in f of x over the change in x. This was f of x plus h minus f of x over, now if you notice, x plus h minus x in the denominator here, these x's cancel, so we're just left with h in the denominator. And if you'll notice, this fraction that we have here is exactly what we have up here. And that makes sense, right? We were going to look at an instantaneous change, so we started with an average change, and the formulas look very, very similar because they're both just changes of f. The only difference is our derivative has a limit. Now, let's draw our attention to that limit. Now, the limit is actually what brings us from the average change to the instantaneous change. When we were doing this initially, we started with two values, right, that were an h distance apart. Now, if I want to look at the change of f at one point, say I want to look at this point right here, what is the change in f of x at just that point? Well, we could say that if we move our h value to here, right, and we make this our new f of x plus h, right, then we moved a little bit closer to that point. And we could keep moving this value closer and closer and closer until it's pretty much right on top of f of x. And the only way we do that is by decreasing h. If we decrease h, every time we decrease it, we get closer and closer to f of x. So what we can say is, as the limit, as h goes to 0, right, we approach, right, f of x plus h approaches f of x. Think about this mathematically, right? If we have f of x plus h, to get f of x plus h to become f of x, we decrease h to 0. So we use our limit, right? Because our limit means as something approaches 0, not that it is 0, right? Because if h was 0, then f of x plus h would just be the same as f of x. But we say as the limit, as h approaches 0 of f of x plus h minus f of x over h, we get the change in f of x at that specific point that we were looking at. And that we can define as f prime of x. Now, I hope you can see that this definition of a derivative is not as complicated as it might seem. It certainly is something that takes a little bit to get your head wrapped around, but the point I want to drive down the most is that the instantaneous change of something is very similar to the average change. It's just that we're taking the distance between the 2 points that we take the average over, and we move them really, really, really close to each other until they're on top of one another. And that's where this limit comes in. And that's why we learned about limits, or you learned about limits before you got to derivatives, because you use limits to define what a derivative is. So, again, an instantaneous change is simply an average change where the 2 points that you start at and you end at move really, really close to each other, and that distance between them approaches 0. In our case, we had f of x plus h and f of x, and we said that this fraction here was our average change. And all we did to turn it to an instantaneous change was to take the limit of it as the distance h between those 2 points, the distance between f of x plus h and f of x, which was h, we just made it so that h got really, really close to 0. And that we could use to define our definition of a derivative right here.